Welcome back, everyone. This is the fourth and hopefully the final video segment for combined section 5.3 and 5.4. What I'm going to do is we're only going to do examples. There's nothing else really derived, but what I am going to start with is just a reminder of the 6 new identities that we have produced. So let me just move over here to my document camera. Just 1 second. Okay, looks like I managed to fix all the focusing issues, but I think part of the problem is the equipment is really not that high resolution, but it's getting the job done. Anyway, so this is combined section 5.3, 5.4. We're now on page 9, and I want to start by just recalling the 6 identities. So we said that cosine of a sum or difference is equal to the cosine of the first angle times the cosine of the second angle. Reverse the SIGN, so minus plus sine of the first angle times sine of the second angle. Okay, so next we showed that the sine of a sum or difference is equal to the sine of the first angle times the cosine of the second angle plus minus, so the same SIGN, times the sine of the second angle times the cosine of the first angle, okay? And then we further derived the relationship for the tangent of a sum or difference. This one's a little more compact, but it has a fraction in it. This is equal to the tangent of the first angle plus or minus the tangent of the second angle, all divided by 1 minus the product of the tangent of the first angle and the tangent of the second angle, plus minus plus. In the last video, when we were deriving the exact value for the tangent of 3 pi over 12, I blew that. I forgot the reversed symbol. And so I've made the correction in the notes, so when you actually see it on Blackboard, you should see that in red. Okay, so just to summarize, these are the 6 new identities. These are the so-called sum and difference identities. You will be expected to know these just like the fundamental identities. Now you can either memorize them, which I would highly recommend, or you can remember how to derive them, which, as you saw, took quite a bit of time. You can derive any of them from one of them, and that's why we proved cosine of A plus B, and then we used fundamental identities and some algebraic manipulation to find the rest. Okay, so this is to try to use this in a particular aspect. I want to do a really simple observation here. You remember how I said a long time ago that if we had the cofunction identities are a special case of these identities, is something that I said. 90 minus a theta, sine of 90 minus theta is cosine of theta. And I said, well, we're not going to focus on this too much because later on in chapter 5, we're going to run into a situation where it turns out that that's just a special case. Let me show you as an example. Let's take something that looks a little bit like a cofunction identity, and see what we can get from it. So let's try to find the exact value of the sine of 270 degrees minus theta. Okay, now this is kind of like a cofunction. It probably ought to have something to do with a sine or a cosine or something. And we could use some of the graphing techniques from chapter 4 to be able to say exactly what that looks like. This is kind of like a horizontal shift to a sine function. But let's use this. Let's use our newfound tools to do this. So recall, for sine a minus b, we have the sine of the first thing, which is 270 degrees, times the cosine of the second thing, minus sine of the second thing times the cosine of the first thing. Okay, 270 degrees and theta. Now, one of these is going to be equal to 0, and one's going to have I think, a minus sign in it. So recall the quadrant angle 270, sine of 270 degrees is actually -1. Here, cosine of 270 degrees is actually 0. And so in some sense, this second term disappears, and all we're left with is minus cosine of theta. So to summarize, this thing that looks a little bit like a cofunction identity turns out to be fairly similar, but it's actually reflected. You can do this with other sort of quadrant angles, and you'll find that there's a whole bunch of somewhat interesting relationships, but it's not all that awesome. Anyways, what I would like to do though is I'd like to show you one that involves a phase shift. So you may recall that previously when we were doing the graphing, we had done some things where we called it a phase shift when the C value is non-zero. That phrase was used maybe once or twice. I mentioned it, but it may not be something you easily recall. But let's just look at some kind of a shift involving, say, cosine. So let's take cosine of x minus pi over 3. Okay, now this is this should look like what the graph of this thing looks like, right? This is the regular cosine function shifted to the right by pi over 3. We're going to show how we're going to get rid of this pi over 3, and we're going to actually find what the equation is for this. So it's a way of turning sums and differences of sines and cosine functions into a single function with a phase shift. This is something that you may see maybe years down the road in a physics class or an engineering course. This sort of backwards process where you go, well, if you're trying to add, some constant times sine and another constant times cosine, then it turns out that it's equivalent to a sine or a cosine with a phase shift. But let's just work through the function. Let's work through the problem. So recall, for the cosine a minus b, that's going to be cosine of the first thing times cosine of the second thing. The SIGN will be different, so plus the sine of the first thing times the sine of the second thing. Now these have exact values, so cosine of pi over 3 is actually 1/2. And sine of pi over 3 is square root of 3 over 2. Okay, and it makes sense to put those out front. So we have 1/2 cosine of x plus square root of 3 over 2 times sine of x. Okay, so notice that what we've got here is that if I add sine to cosine with a different with differing coefficients, I can actually create a cosine that's just a phase shift. This is something, and I don't want to scare anybody away, but this kind of stuff comes up in quantum mechanics everywhere. So if any of you have any hankering to ever do any sort of advanced physics, you will see this again, and hopefully you'll think back, gosh, I remember when that crazy instructor told me about this, or maybe not. So those are a couple of examples of things where it's not quite known values, but something similar. Now, what I would like to do now is I want to create a sort of a step-by-step process that is going to look a little bit familiar from the kind of stuff that we did in chapter 1. You recall in chapter 1 we did things like, and let me just kind of put this as an aside. So recall that in chapter 1 we did some problems where it was like, given I don't know, say sine of x equal to 1/3 and x in quadrant 2, find some other function, like say tangent of x. And we proceeded by saying, well, okay, here's a way we can do that. We can draw an angle in quadrant 2. We can then assign a point on that terminal ray that's a distance 3 from the origin and whose y value is 1. Fill out the remainder, the other side, which I think in this case is going to be square root of 8, so 2 root 2, negative 2 root 2. So we would kind of draw here's the angle in quadrant 2. It has a point P with a y value of 1, r equal to 3. You'll find if you do this that the x value will be negative 2 root 2. Okay, and so if you wanted the tangent, well, the tangent is going to be 1 over minus 2 root 2, which turns out to be, I believe when you simplify that, so tangent of x will be equal to 1 over the negative 2 root 2. So simplifying, multiply by root 2 over root 2. And I believe we end up with negative square root of 2 over 4. Yeah. Okay. So this is kind of a repeat of where we were a while back. Now, what we're going to see in chapter in these two sections is you're going to see some problems where you're given certain information about one of the angles, kind of like this sort of setup, and then you're given something about another angle, which is going to look just like this problem, only a different set of parameters, and then you're going to be asked to find, like, say, the sine of the sum or the cosine of the difference. Okay, so but this fundamentally, this process you're seeing from chapter 1 is what you end up doing, except you end up doing it twice to find whatever kinds of values you need, and then you use these sum and difference identities to sort of finish off the task. So let me just start with a fresh sheet of paper, and I want you to take a quick gander at a problem. I'll just write it up here. So let's see, section 5.3, 5.4, page 11. Okay, so let's state it this way. How about let cosine of A equal negative 7 over 25, where A is in quadrant 3, and sine of B equals negative 3 over 5, where B is in quadrant 4. Okay, and let's say that we would like to find couple of things. Let's find sine of the difference. Let's find maybe say tangent of the difference. And also, let's maybe do a sum in here. How about cosine of the sum? And maybe what quadrant the difference is in, because I'll know enough by doing these here. Sort of a shorthand. Find the quadrant of the difference, A minus B. Okay, so let's start with task number 1. Now, what we know that these formulations for the sum and difference of sine have both cosine of A and cosine of B, sine of A and sine of B in them. So we need to find those values. And that's sort of what I was saying. We have to solve this problem first and then this one. So now that's for the sum and the difference of both sine and cosine require you to have sine A, sine B, cosine A, cosine B. We also, for this difference of tangents, we need the tangents. So what I'm going to do is I'm going to solve this problem here, given cosine of A equal to -7 over 25 with this quadrant, find sine of A and tangent of A. This is sort of the process that starts. So I'm going to say find sine of A and tangent of A. Okay, so remember, what do? Well, we start by drawing our angle A, which is in, according to this information, is in quadrant 3. And because cosine is -7 over 25, that's the R value and the X value. Right? So what's the Y value? Well, the Y value is going to be equal to the negative square root of R squared, which is 625, minus X squared, which is 49. And if I'm not mistaken, I think this comes out exactly to 24, negative. Notice that negative sign is because of the quadrant that it's in, right? So I think that's right. You can check me on that, but I'm going to assume that it's true and go on. So based on this information, I now have X, right? I could maybe say X equals, and I have Y, and I have R. So I should be able to find any trig function I want from their definition. So what was I after? Sine of A and tangent of A. So sine of A is equal to, well, it's the Y value over the R value. So that's -24 over 25. And tangent is the Y value over the X value, which happens to be -24 over -7. The negative signs cancel, so we're left with 24 over 7. Okay, so this was kind of first step. Get these values, because we're going to use them in a little bit. So now go back to the second piece where I have the sine of B equal to -3 over 5 with B in quadrant 2. What am I going to need? Well, I'm going to need, similar to this one, I'm going to need cosine of B and tangent of B. So let me just write that as a second problem. So now find cosine of B and tangent of B. Okay, so same thing as before. Start by drawing your coordinate axes, and it is B is an angle in quadrant 4. So let's make sure that's in 4. And we know that based on the fact that sine of b is -3/5, that means that there is a point on that ray where the r value is 5 and the y value is -3. So we'll just think y equal -3, r equal to 5. And I think we've done this particular setup enough times that hopefully you'll see that x is equal to 4. But I'll go ahead and show it. So x is going to be equal to this positive, no, because it's in the either quadrant 1 or 4, positive square root of r squared minus y squared, which happens to be equal to the square root of 25 minus 9. Which, as I hoped, comes out to +4. So now we have x, y, r, and we can write any trig function for this angle. So we wanted cosine of b. Well, cosine of b is x over r. So that's 4/5. And tangent of b is y over x, so -3/4. Okay, so that was the setup to be able to even start doing the problems. So I'll kind of hold this one in reserve. So that was sort of some preamble that we needed to do in order to be able to do the rest of it. So section 5.3, 5.4, I think we're now up to page 12. Okay, so we now want to find sine A minus B. Okay, well, recall the formula for sine of a difference is that this is equal to sine of A times cosine of B minus sine of B cosine of A. Okay, that's our difference formula. Now, I'm going to push this right to the side here because there's some of those values. And in the problem statement, we were also given cosine of A and sine of B. Okay, so sine of A is equal to -24/25, right? Cosine of B was 4/5. Minus sine of B was given in the problem as -3/5. And cosine of A was given in the problem as -7/25. So when we simplify this, I think you end up with -96/125. Let's see, minus, so minus 21/125, which equals a grand total of -117/125. So this is sine of A minus B. Bang, bang. Let's do the tangent. So now we want to find tangent of the difference. I think my markers are about had it here. Let me move to a Sharpie. I bought some Sharpies at the store because Amazon isn't really delivering, but I did manage to get to Costco. This one's actually an old one. Hopefully it holds together. So recall the difference formula for tangent was it is the tangent of the first angle minus the tangent of the second angle. Oh, that didn't work at all. Divided by 1 plus the product of the tangents. probably going to go back to my other marker here because this one is really shot. Okay, so remember, with this sort of scratch work we did before, we came up with the value for tangent of A and for tangent of B. So this will equal, let's see, tangent A is 24/7 minus tangent of B, which is -3/4, okay? All over 1 plus 24/7 times -3/4. Okay, this is a pretty ugly complex fraction. And so what I would suggest is that we simplify that using method 2, which is to multiply all terms by the least common denominator of all the interior terms, which in this case is going to be 7 times 4 is 28. So I'm going to multiply everything in here by 28, my simplification process. And here's what I end up with. The 28 will kill off the 7 and leave 4, so we end up with 96. This is a negative of negative, so that's a positive. 28 times 3/4 is going to be 7 times 3, so this is going to be plus 21. In the denominator, 1 times 28 is just 28. And this 28 will kill off both of these denominators here, and you're just left with 24 times -3, which happens to be -72. Okay, so what does that reduce down to? We end up with, when it's all said and done, we get a 117 over -44, and I'll just bring that negative sign out. So -117 over 44. Now, to be fair, if we knew what quadrant this thing was in, we could have done this just by knowing what the sine of A minus B is and doing the same kind of process like what we did at the very beginning. So, but we didn't know the quadrant. However, we do now, because you have a situation where the sine of the angle in question is negative, and the tangent of the angle in question is negative. So what quadrants are both sine and tangent negative? Well, that only occurs in quadrant 4, okay? So we can jump to that last question and actually answer that right now. We can say that, let me get my heading started here. 13, okay. So what quadrant A minus B? Sort of a shorthand. Well, note sine of A minus B is less than 0, and tangent of A minus B is less than 0. So A minus B is in quadrant 4. Okay? The final task we were asked to do was to find the cosine of A plus B. And recall from the sum formula for cosine that that is cosine of A times cosine of B, different sign, minus the sine of A times the sine of B. All right. So going back to the values that we determined, cosine of A is -7 over 25. Cosine of B we found down here was 5 over 4, or sorry, 4 over 5. Then minus sine of A, we found is minus 24 over 25. Notice I'm being really, really careful with these parentheses because this is what happens is you have all these negative of negatives popping up everywhere, and it pays to just be very meticulous. Finally, sine of B was given in the original problem, which is minus 3 over 5. So multiplying everything out, we have minus 28 over 125. Minus, 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 so this would be minus 72 over 125, which I'll be dipped. Look at this. This is going to be minus 100 over 125, which reduces down to negative 4 over 5. Which is crazy because that's happens to be equal to negative cosine of B. So there might be some kind of interesting thing going on there. I think I did that all right. I didn't have notes on this one. I just kind of did it on the fly. If you see something wrong, when we're in class, it's easy for me to catch mistakes. But I mean, gosh, if you see some mistakes, ask for clarification, and I'll try to do that. But I think that there will end our discussion from 5.3 and 5.4. You've seen at least one example of the kinds of problems that are in the homework for this section. If you have any questions or concerns, feel free to drop me a message, and we'll see you around.